First of all, I would like to thank the organizers for the invitation and especially for organizing this whole program. I guess it must have been a bit frustrating to postpone it twice, so thanks even more. I thought I would be not the only one talking about Glauber dynamics, but Eyal is talking about something else. So initially I thought he would talk about positive temperature Glauber dynamics, and I would concentrate on zero temperature. Then I decided to do something a bit broader. All right, so this is the plan of the talk. We have seen a lot of Ising model, obviously, but not so much about dynamics. It was briefly mentioned by Roland. So I will introduce that, just to make sure we all know what it is. Then I will formulate some of the, say, big questions in this area. I'm not claiming I will be solving any one of them, but there are some progress. Then I will concentrate on somehow a more special situation, which is the zero temperature dynamics of the Ising model, which is still quite non-trivial and actually mathematically very aesthetically pleasing, I would say, even more than the non-zero temperature. And I will show the connection with random tilings, which is probably very well known to many of you, but still. And then come to some results, old and new, about mixing times for the zero temperature Glauber dynamics. So I will be mostly in 3 dimensions, but 2 dimensions will also appear also for like comparison, etc. Okay, good. Let's start. So I will not reintroduce the Ising model. Let me just make sure. Maybe some notation. So anyway, so I'm looking at the classical ferromagnetic nearest neighbor Ising model on ZD. I will denote P the equilibrium measure with the index by the inverse temperature. The V, the box, could be infinite. The box, could be the whole of ZD, and the boundary conditions tau on the boundary. Okay. Good. What we will be interested in is a dynamic, so a stochastic process evolving in time. I will call sigma of t the configuration at time t, and this stochastic process will be Markovian in time. Will be the Gibbs, the usual Gibbs measure will be reversible, stationary and reversible with respect to this process. And somehow we want a process that is physically, say, natural in the sense that, for instance, update rules are local. They just look at the local neighborhood. So there are many ways to implement this, actually, infinitely many ways. You can look at metropolis type of algorithm. The example, the one I'm looking at here is another very classical example. It's called the heat bath dynamics. So it's a continuous time process. It's not, you could do it in discrete time, but we'll do it in continuous time. You can see it as follows. Every lattice, every vertex in your graph has an exponential clock that rings at random times. That the time between 2 rings is exponential, and these clocks are IID. And when the clock somewhere rings at x, what you do is you resample the value of sigma at x, and you do as follows. You resample sigma x at t from the equilibrium measure conditioned on the value of the spins outside of x. This is what you do. Okay. The boundary spins obviously don't evolve, so there are really boundary conditions fixed once and for all. The updates are really single flip updates. Every time you update a single spin. So this is very different from Swensen-Wang type of algorithm where you would flip the entire clusters. Very different. Also very interesting, but I'm looking rather at this single flip dynamics. Okay, I hope the definition is clear. I didn't write down the generator, but this is you can do. All right, so here just an example. Suppose so here black and red means plus or minus. You have some portion of your here 2-dimensional graph. A clock here at x rings. So you forget the value of the spin at x, And then you want to resample that. Since you want to resample from the equilibrium distribution given what is around, since we are looking at the nearest neighbor model, only the value of the neighbors matters. So the other ones, okay, I don't matter. And then here in this particular example, you see 3 minuses around and 1 plus. So you sample a new value of the spin given these 4 neighbors. In this case, it's more likely to have minus. I think it's eta to the 4 beta more likely. So okay, in this example, in fact, you've sampled minus. You could have sampled plus. It's just much more unlikely if beta is large. Okay, so this is how it works, and then you proceed. All right. Okay, a couple of comments. First of all, the dynamics is well defined, no problem, even in infinite volume, in infinite graphs. This is very standard result, maybe by Liggett. So I mean, you can define the dynamics in infinite volume without any problem. In particular, updates are really never happen at the same time in 2 different locations, simply because the clocks have continuous distribution. Okay, so this. The other thing, which will, okay, you will not see the role of this remark in the talk, but it's crucial that the dynamics is monotone. Because I'm looking at ferromagnetic, what happens is that if you look at 2 different initial conditions, one higher than the other, so higher means pointwise at every site, the usual order, usual partial order for the Ising model, then you can couple the 2 dynamics so that this ordering is preserved in time almost surely. There is a very natural coupling between the dynamics. So this is really essential in all the proofs, even though I will not show any proofs here, but this is as essential as FKG when you want to prove equilibrium type of state.
Actually, I don't understand. What does it mean under natural coupling?
Well, essentially, what you have 2 initial conditions. You could let evolve, for instance, independently, and then obviously the things is not preserved. But what you do is you use the same clocks for the 2 processes. And secondly, when you update, you use the same coin flips. So there is, yeah, in natural in this sense, you have to, if you use independent clocks, obviously this will fail. Yeah. Good. So maybe this is important. This is not, this Glauber dynamics is not the fastest way you can use to sample the Ising model for sure. For instance, Swenson 1 is more efficient. But on the other hand, it's more natural if you think of a real physical system evolving with local interactions, then it's, in this sense, it's more natural, more realistic, if you want. Okay. All right. So, what kind of, why could one be interested in this, in understanding these dynamics? There are at least 2 very different points of view. The first one is to view the Glauber dynamics as a way of simulating the equilibrium measure. In that respect, it may be useful in that case to look at the fastest type of algorithm, which I'm not doing. And in that case, you may be interested in how fast the dynamics reaches equilibrium. I will define later a mixing time, but you can imagine that you have this stationary distribution. At least in finite volume, you will certainly reach it asymptotically, and somehow you can quantify how fast you reach equilibrium, and then you want to somehow to estimate it, for instance, as a function of the size of the system. Okay, so this is the first type of point of view. The second one is to understand the large-scale behavior of motion of boundaries between coexisting phases. So what does this mean? So we all know that in dimension at least 2, at low temperature, there are at least the plus and the minus pure phases. And what you can do is you can prepare your system initially in a state where you have a droplet of, say, minus phase surrounded by plus spins, and then you let the system evolve, either your real magnet or your Ising model. And then you expect this droplet to, you expect the system to try to minimize the boundary between the 2 phases, that it's costly. So this droplet will evolve in time, and then the question, how does it evolve? Does it expect it somehow to shrink, but not to disappear immediately? So it's interesting to try to understand the motion of this boundary. Okay, so these are the 2 types of motivations. I came to this whole area more from this second point of view. Okay, good. So here are some of the, say, big questions in this area. So the first one is so-called coarsening. This can be also described as like order emerging from disorder spontaneously just by letting things evolve. This is something you will not observe in your children's bedroom, but it happens for Glauber dynamics. So if you start from something very disordered, but you run the dynamics at low temperature, you know that eventually the equilibrium measure will be ordered. So mostly plus, or mostly minus. So what will happen is that as time goes on, the pluses and the minuses will aggregate more and more, and you will see these structures, here black and white means plus and minus, this structure that gets thicker and thicker. Somehow you have this typical length that grows with time. This is what coarsening means. This is something that mathematically is very far from understood. And by the way, I have no results about this. I just wanted to mention this question of coarsening, but I have nothing new about it.
Can you say what some of the conjectures are?
I think in 2D, one expects that the typical length scale grows like square root of t. And there are other conjectures which are very natural. That is, if you start from Bernoulli p with p different from 1/2, say larger than 1/2 strictly, then you should converge. Okay, say at zero temperature, you should converge locally almost surely to the plus, say. But this is proven only for p very close to 1. So there are even this, and then there are conjectures. I think one thing that is proven is that if you start from p equal 1/2 and you are at zero temperature in 2D, things flip infinitely often. This is, I think, is proven by maybe Newman, yeah. But many basic questions like for p equal 0.51, do I converge to +1? Or this is very completely open.
Yeah, sorry, why? So don't you have convergence to the equilibrium measure?
Yeah, but suppose suppose you're infinite volume here. Yeah, so suppose you're infinite volume and you start from Bernoulli, so independent spins.
No convergence in infinite volume.
Well, the question, yeah, what you could. Yeah, exactly. So if you fix a finite window, it could happen that spin still continue to flip infinitely often, even though the density of spins plus is 0.9, which should not have. It should just fixate to +1. Of course, in finite volume, depends on the boundary condition. But, yeah. Okay. So another question is related to this motion of the droplets. What one expects here. Again, so you're in this situation here, and you imagine this droplet to be very large, or maybe you take the lattice mesh to go to 0. And then in this limit, and then you rescale time properly, in this limit, you expect this droplet to evolve in time somehow continuously, in the scaling limit to be given by some continuous domain, sigma t, that evolves in time. And the general type of behavior you expect is that the normal velocity at the point of the boundary, so this is a normal vector, and normal velocity will be proportional to some coefficient that depends on the orientation, local orientation of the local normal vector. It is called mobility, times, something that is simply the first variation of the surface energy functional. So f is just integral over the boundary of the droplet of the surface tension that depends on the orientation, okay? And then what this is saying is that the interface will move in the direction which tries to decrease the surface tension. Okay, the minus is just because of the sign I've chosen. Okay, so this is telling you that this droplet will should decrease, but somehow in a way that is somehow. In this type of way. By the way, if I, instead of looking at the Ising model of the lattice, we are looking at somehow a continuous model that has rotation symmetry, one would expect this mobility and the surface tension to be just constant, independent of the direction, because there is no lattice. And then this motion would be simply motion by mean curvature, something that decreases the surface. But because we are in a lattice, anisotropy effects will be there, and one expects some non-trivial dependence on the local orientation of the surface. Okay, so this is the type of behavior one expects, And there is a case where that one we could prove it is 0 temperature in 2D, but I will not talk about this result, but if you're interested, I can tell you. Okay. Right, and then the third type of question concerns mixing times. So again, mixing time will be defined later. But the type of question one is interested in here is how does the mixing time grow with the system size V, the cardinality of the box. And there is a non-trivial dependence both in the temperature, in the space dimension, and in boundary conditions. So here I try to squeeze into a slide many, okay, it's certainly not a full list of references, but at least I want to flash some of the important progress that was made in the past. First of all, if you look at your system at low temperature with periodic boundary conditions, then what you expect is that if you start, say, from the plus phase, it will take a long time before the system equilibrates because the system is symmetric between plus and minus. In order to make a transition to the minus phase, it has to overcome some energy barrier that is costly. It costs like something like L to the D minus 1. So, okay, and then, so in fact, it is known that, in fact, with at low temperature, with plus boundary conditions, equilibration is very slow because of this barrier between plus and minus boundary phases. And yeah, and there is a metastability. If you stay very long in the plus phase, and then after exponentially long time, you make a transition to the minus phase and back and forth. This is the type of things that happens. On the opposite side, for beta smaller than BC, relaxation is fast. This is quite intuitive and actually quite easy to see, to prove if beta is very small. But to cover the entire high energy, high temperature phase is highly non-trivial. And for instance, in the works by Lubetzky and Sly, it was proven that in this whole region, you have fast relaxation, but also what is called the cutoff phenomenon. Okay, I have no time to introduce what it is, but then you can be at a critical temperature, and here it's known in dimension 2, and thanks to this very recent work that was mentioned by Roland yesterday, by Roland and Benoît Dagalier, it's known also in dimension 5 and higher, that at the critical point, the mixing time is polynomial in the system size. Good.
Why is it that 2 and 5 or more dimensions are special?
2 is special because the proof relies on estimates on like Russo-Seimer-Welch type of estimates by Dumesnil-Copin and Clement and I forgot who other. So 2 is special in that respect. 5 is special because this expansion works. But and then 3 and 4, I think in 4 you have quasi-logarithm, quasi-polynomial, and 3, well, no one. I mean, it's a problem of equilibrium estimates. I would say. Right, good. So it is my answer. Yeah, so they work for 2 different reasons. I think in none of the 2 cases the exponent of the polynomial is optimal. It's just some polynomial. Oops. Okay, so sorry, I went the other way. Yeah, another thing that you can look, it's a nucleation. You start from you have a small magnetic field. So you have a unique phase, so very small positive magnetic field, but you start from the minus phase, and then it will take time before the plus phase nucleates, and then you can study how long that takes in terms of this magnetic field, and this was studied, for instance, by Schoenmann and Senya. Yeah, there are many things that were done about mixing times on spectral gap. This is a partial list. Okay, so now...
So low temperature with plus boundary condition is not only in 2 dimensions?
Okay, so I skipped this one. Low temperature plus boundary condition, one expects in all dimension L squared mixing the relaxation time of order mixing time of order L squared. It's known in no dimension, but in 2 dimension, with Eyal and Allen and Martinelli, we know almost that. We know that almost a polynomial bound on the mixing.
So in all dimension is not...
It's conjecture to be L squared in all dimension. In 2 dimension, we have L2 log L, and in 3 and higher, bands are just too bad. So.
which means exponential.
I think in 3D it's like e to the square root of L or something like this, or e to the L to some 2 over 3. I don't remember. Something barely better than trivial. Yeah, but this was huge. I mean, huge technical pain even to get almost quasi-polynomial. Yeah. Anyway, so it's nice to move now to 0 temperature. The process becomes much cleaner, still highly non-trivial, but much cleaner. So at 0 temperature, so beta equal infinity, things the process is can be redescribed as follows. Every spin has an independent IAD exponential clock. When it rings, you just look at your neighbors. You have 2D neighbors. If there is a majority of one of the two signs, then you update that spin to that majority. But since the degree of the graph is even, it could happen that there is a tie. How do you call it? And then in that case, you just flip a coin, a fair coin, independent of whatever has happened before, and then you decide your update like that. And
you say since the degree of the graph is even, but
I could be on a hexagonal lattice. Yeah, but in that case, there are also some, for instance, if you had on a honeycomb lattice, then this doesn't happen. But in that case, there are other things that are a bit annoying that you can get stuck. Like if you have, it's a different phenomenology, but it's very unstable to temperature. So, and anyway, so all the results will hold for ZD for other reasons that we really need ZD. But yeah, you're right. If the degree were odd, in that case, there would be no randomness except the initial condition, but new phenomenon. It's 0 temperature is quite sensitive to, so it's very different phenomenon. You can have this block configuration, etc. Yeah. So here is an example. So in this case, you are in 2D. We update this central spin. In this case, we have 3, say, minus spins around. We have no choice. We put minus. In this second example, we have 2 and 2, and then we can flip a coin. In this case, we put blue. I don't know what that was. Okay, so there is still randomness when you have to flip the coins. Of course, there is also randomness in the ringing of the clocks. Okay, good. So now 0 temperature. So what is the stationary measure? Well, stationary measure, say infinite volume, is simply the uniform measure over all ground states, where ground states means simply the configuration that minimizes the pairs of sides with opposite signs for the spins. Now, in infinite volume, you can have block configuration like strips of pluses surrounded by minus are stable. But let's think of finite. Let's think of finite volume. So this uniform measure can be either trivial or not. For instance, if you have plus boundary conditions, then obviously the only ground states are all plus. So in that case, the equilibrium is totally trivial. It's a Dirac mass. But it can be non-trivial. If you look at Dobrushin-type of boundary conditions, like here, tilted, it is important. So you have plus on one side and minus on the other side, but somehow this, it's tilted this way. Then all the configurations which are plus and minus like this with this monotone path separating them, these are all ground states. There is a huge degeneracy. It's like order e to the L exponentially in L number of configuration. They are all equiprobable. And so it is already non-trivial. If the thing is horizontal, then there is just one configuration. So it's still non-trivial, but still is some very, very well-known measure. This is simply a random walk bridge with fixed. You fix the endpoints, and then you have just a random walk bridge. So still, it's something we know. But things become much more non-trivial in higher dimensions. So here is a picture in 3D. Imagine you have a cylinder, and you take Dobrushin boundary conditions. So I intersect with a plane, and I say I'm on the boundary I have minus above and plus below. And then there will be an interface separating plus minus. And a bit like this upgoing path, you will have an interface like this. So in this, I found this picture. So in this case, you have to imagine that cylinder has a triangular section.
So it's a prism. So a prism.
Yeah, a prism. Yeah, thanks. And in this case, it has been intersected with a 1, 1, 1 plane. So you have this these are the minimal, the walls between plus and minus that minimize the energy. And if you look at it a bit, it's a bit like this path are only going up. Also here, in both directions of space, you will see that this height just goes up. This is what minimizes this boundary between plus and minuses. But you see, this is already much more non-trivial. Okay, good. So this is about, so these are what the stationary measure looks like. There are uniform measure on this configuration. In higher dimension, it's even, I have nothing to say in higher dimension, but you can imagine this even more complicated. Now, there are many things one can say about these surfaces that we just saw in this. Okay, random walk bridge, we know everything, but this we don't know everything. It's much less trivial. So let me try to summarize in one slide. Many facts, many non-trivial facts. So the first thing is that you can view this discrete 3D or maybe 2D interface in 3D as either as a discrete interface, as you see it, or as a tiling. So you have a region of space that is determined by the boundary condition. And then if you view it like this, as a two-dimensional thing, it's just a tiling of a region of the plane by three types of tiles that are rhombi, just oriented in with three different angles that are drawn with three different colors just for clarity. Okay, so all these ground states for the 3D Ising model with the Dobrushin boundary conditions can be seen as rhombus tilings of a region of the plane. Okay, and then we're looking at the uniform measure on these, and then there are many non-trivial facts about this uniform measure. The first one is a so-called limit shape phenomenon, or law of large numbers, that was discovered, I think, by Kohn, Larsen, and Propp, if I'm not mistaken. What it says is that if you look at this surface and you let the lattice mesh go to 0, lattice mesh means the size of this rhombi go to 0, then for the typical configuration, the height function will be deterministic, essentially. So like for the random walk bridge, if you rescale the two dimensional space, the lattice mesh to 0, you just see a straight line. In this case, you will see some deterministic surface emerges. So here, okay, it's not yet in the limit, but you already see something kind of looking deterministic here. You see this kind of circle here. Okay, so the statement is that in the limit where the mesh goes to 0, the typical height function will be concentrated around a non-random shape called the limit shape. This limit shape minimizes the surface tension functional. Okay, and then one thing is to say that there is a unique limit shape. One thing is to find it. So to find it in principle, you have to solve a variational principle. So uniqueness and so on is kind of soft. You have a convex thing. But another thing is really to find it. And okay, one other phenomenon you see here is that in some cases, this limit shape will have some portions which are just flat, which look just deterministic. These are called facets. And in fact, one can describe the boundary of these facets, the boundary of these frozen regions. They are called frozen boundary, and they turn out to be algebraic curves. Like this is a disk. In this case, we'll get a disk. In this case, you get a cardioid, I think, like a degree 4 algebraic curve, I guess. So, and this can be described by there is a beautiful work by Kenyon and Nakunkov describing these frozen boundaries. Okay, so this is another feature you find in these tilings, somehow separation between phases where still you have a lot of fluctuations and regions where fluctuations are almost absent. These are called the frozen phases. Another thing that is well known is that correlations in these measures are determinantal. So if you want to know what is the probability of finding a blue rhombus here and a blue rhombus there and a red one here, this can be written as a determinant of 3 by 3 determinant, on which you can apply then asymptotic analysis, etc. So this was essentially comes from basically from works in the 60s by Kessel and Templer and Fischer, but was very much developed in particular by Rick later. So I mean, one thing is just to say you have determinants, one thing is to do something out of it. About height fluctuations, what happens is that when you are inside these disordered regions, the height function suitably rescaled, say, so suitably smoothed out, tends to a Gaussian free field, a two-dimensional massless Gaussian free field, up to some stretching, so to speak. While, in the frozen regions, you have no fluctuations at all. And at the boundary between frozen and liquid and rough regions, you have so-called Cardar-Parisi-Zhang fluctuations for the interface lines, which are related to, I mean, it has the same type of fluctuations as top eigenvalues of random matrices and so on. So the message I want to convey here is that these measures, even though they are just uniform measures on something, they are extremely non-trivial. There are beautiful phenomena, kind of well-known now. Okay, fine. So, but this is just about the equilibrium measure of our dynamics. Any question about these pictures?
Yeah, I have a question.
Yes.
So when you talked about limit shape,
Yes.
and then you started saying that there are actually fluctuations around this limit shape. So limit shape is what, the average of these fluctuations? How is the limit shape defined?
Yeah, you take, I don't define a height function, but it's kind of obvious there is a height function here. Yeah. And then what I'm saying is that if you have rescaled your cubes to have a size delta, then you look at this height function now of x, say, look at the hexagon. So now x would be in the unit hexagon. So you have this height function that depends on the discretization and depends on x in this unit hexagon. This is random, and I'm saying that it converges in probability as delta goes to 0 to some phi of x under the uniform measure. And this phi of x so now phi of x is a function on the unit hexagon. You can see as a graph of the function.
Okay, but then what about fluctuations? There are no fluctuations?
No. This is the limit shape. So this is like law of large numbers. Then if you don't take the limit and you look at what you can see is that essentially this thing minus the limit is a Gaussian free field.
Okay. Appropriately rescaled.
You don't have to rescale the height. The height you don't have to rescale, but for instance, if you take this thing and sum it against a test function, then this tends in distribution to the Gaussian free field up to a certain stretching against the same test function. You don't have to rescale the typical height. The typical height of the fluctuation is square root of log delta. But if you rescale by square root of log delta, you don't get anything. The limit is a distribution, so.
Okay.
Yeah.
Thanks.
Also, the shape is one-sided somehow.
What do you mean?
It is that somehow you never cross the, you have this circle and you never cross it on this.
Okay. So, well, I mean, no, well, you can, I mean, what do you mean? So you have this circle. Okay, now. Yeah. Well, yes. So, well, obviously not where the circle is tangent to the boundary, but here you can cross it. The probability of, and actually the highest curve has, well, yeah, you can cross. It has fluctuations of order L to the delta to the minus 1/3.
KPZ.
Yeah, it's a KPZ type of, yeah. Okay, any other question on this picture? I didn't want to write, theorems, but. Okay, so now, so the message here is that these equilibrium measures are highly non-trivial, but in a sense very well understood now. There are many experts, even in this room, apart from Rick, say Cedric, Beatrice, Dima. A lot is known. Plus, there is a whole so-called integrable probability community, say Johansson, Borodin, etc., studying this type of question. But it's not because the equilibrium measure is somehow exactly solvable that the dynamics is. So, in fact, the equilibrium measure is determinantal, as I mentioned, but the dynamics, this Glauber dynamics doesn't have determinantal formulas for space-time correlation. So this is important. Okay, so let's come back to the dynamics. Remember, we are looking at the zero temperature dynamics, say, of the 3D Ising model with this type of boundary conditions. And if you look at what the updates do, all what happens is that when you, okay, so here you have these cubes that represent, say, the plus spins, and what is empty is minus spins. So flipping a cube from plus to minus in terms of these tilings means that you are like moving around 3 types of rhombi locally, like you do this type of rotations. So it's like you have these particles of 3 colors that are interacting and they are exchanging the positions, but in a very non-trivial way, because, for instance, they can do it only when 3 of the different colors meet. So it's not, yeah, I mean, you can view it as a system of interacting particles, but it's not a particularly simple one. Or you can see it as an evolution of a discrete height function. All right, so let's come to move towards the results. Let's define now at last the mixing time. All right, so I will define, let's think of this Glauber dynamics, but this definition is very, very general for Markov chains. So in our case, this mixing time will depend on the okay, sorry, here, well, now we're at infinite beta, so forget the beta. Depends on V and the boundary conditions. What is the mixing time? It's the first time at which your dynamics is close to equilibrium in total variation. So you have to take the maximum over all the initial conditions, and you want that the law at time t with this initial condition is a distance at most, say, 1/4 in total variation from equilibrium. Okay, so mu is the law of the process at time t with this initial condition. This thing is the total variation distance, kind of L1 distance between probability measures, and 1/4 is some conventional number. You could choose 1/8 or anything smaller than 1/2. It's just telling you that you are close to equilibrium. And it's important here that you are taking the worst case on boundary conditions, which is usually very annoying, because usually you have to exclude that for some very unlikely initial condition you get stuck somewhere. And it's in this case that monotonicity helps a lot, because since you're monotone, you can just care about the extremal boundary, the extremal initial condition where you're all plus or all minus, and if you can control those, and everything else is in between. Here, in this sense, monotonicity is a huge help. Okay, now conjecture. So the conjecture is that actually in every dimension, the mixing time will be of order L squared, where L to the 2 plus little of 1, where L is the diameter of the box. So you think of the diameter of this. You have this cylinder, you cut it, and somehow the section of the cylinder has diameter L. And then you expect this behavior. So this exponent 2 is supposedly independent of dimension. This is important. It's corresponds to so-called diffusive scaling. In dimension 2, we will see in the next slide, is actually this result is not a conjecture. It's actually a theorem which is not particularly hard to prove. In fact, in that case, one can prove that the mixing time is of order L squared times log L. So these O1 corrections are really there. So.
Can you remind us how is the variation distance defined?
Yeah, you have to say to probability measure on a discrete state space, and then you define this as the max over all events of you can define in several equivalent ways. This is one. Yes. Any other question? Okay. So next slide should explain you why dimension 2 is easy and why. So at least in that case, you see the L squared. So in dimension 2 is particularly easy because if you just take your picture and rotate by 45 degrees, the boundary between plus and minuses just becomes this simple random walk path. Okay. And then what is the dynamics doing? All what can happen is that these minima flip to maximum, and the maxima can flip to minimum with rate 1, say, or 1/2 or whatever. And then this is a actually can be mapped to a very well-studied, maybe the most well-studied interacting particle system, which is symmetric simple exclusion that looks as follows. You associate to every upgoing part of the curve of the boundary a particle, and every downgoing one a hole. And then this, you can have at most one particle per side, obviously. And then this particle jumps, when you do a minimum to maximum flip, the particle jumps left. And when you do the other one, the particle jumps right. And the dynamic is done in a way that particles can never jump on top of another particle. This is why it's called exclusion. It comes simply from this rule. Okay, now this process is super well studied. I mean, there are still maybe, not everything is known, but very much of it is known. And in particular, what is known is that if you look at the height function, so here you have this height function as a function of the horizontal coordinate, you have h of x. If you take this height function and rescale space and time diffusively, so you take like the lattice mesh going to 0 if you want, and you accelerate time by the square of the inverse lattice mesh, this is what I'm doing, and divide by L. Then this random height function tends, as like L goes to infinity, to a function h, say capital H, that is now deterministic and solves a PDE, which is simply the heat equation. Okay, so this is actually not hard to see, even to prove. Okay, so it's important here that you see this scaling L squared. You have to see a macroscopic evolution, you have to take times over the L squared, which is consistent with this L squared here. Now, if you want to understand the log here, it's slightly more subtle, but not too much. The idea is that okay, essentially what you want to say is that okay, yeah, I don't know. Do you want to know? Now, the point is that to really reach equilibrium, you have that the interface has to be very close to almost flat, and to have the typical height of the fluctuations, which are square root of L. So if you pretend the height function is really evolving according to heat equation, in order for it to, starting from a height L to reach square root of L, it will take a time log, constant log, and this explains the log. Okay, so this is, if I had a few minutes more, I would do it, but.
I'm a bit confused, Fabio.
Yes.
Shouldn't you have divided by L squared in the argument of H?
No. I want this. I shrink. I change the. No, I don't. So I want to. The lattice. Okay. This first rescaling is simply I'm rescaling the mesh size so that the interval is now 0, 1. Say, and the non-trivial thing here is that I'm not rescaling time with the same factor, but with the square of it. So it's like, suppose you have a single particle in the interval 0, L. Then what you do to see convergence to Brownian motion, you want to rescale the space by L, so to be in 0, 1.
Yeah, I understand. Okay, I understand. Thanks.
Yeah. Okay. Now, what about higher D? Well, unfortunately, there is no mapping to an easy or solvable interacting particle process like simple exclusion. But conjecture is, even in, say, in 3D, one conjectures the height function rescaled in the same way to converge to the solution of a certain PDE, which will be still parabolic, like the heat equation, but in general will be nonlinear and, nonlinear. And this is very conjectural. And of course, the limit shapes, as I mentioned before, will be just the stationary solution of this PDE, so we just solve right-hand side equals 0. Yeah.
Since it is conjectural, you must have a reason to conjecture.
Yeah, well, the idea is really that locally you want to minimize, actually, so this right-hand side will be simply given by a mobility factor that you can guess from Green-Kubo formula, times a term that gives you, it's like the how do you call it? The gradient flow with respect to the surface energy functional. So what you expect is that you have the interface somehow, and it will tend to flatten, and you can compute the speed at which it flattens by computing how much this decreases the surface energy. But in front of this, so this is something that is purely an equilibrium effect. But in front of it, you have this mobility, mu of gradient of the height. And this you can compute from, at least formally, from Green-Kubo formula. Okay, good. So let's see what is proven. First of all, before looking at L to the 2 plus little of 1, you can even wonder, will the dynamics converge in polynomial time or in exponentially large time, etc.? So this is the typical question of fast or with respect to slow mixing. And for this random tiling dynamics, this was solved around 20 years ago. It is okay. Somehow you have a huge, your state space is huge. So there are, if you look at these regions of size L, there are exponentially over L squared, mainly for configuration. So it could take very long before you reach equilibrium. But something that was proven in a very nice paper by Luby, Randall, and Sinclair is that the random tiling Glauber dynamics, or the zero temperature 3D Glauber dynamics, converges in a time that is at most polynomial in the size. This is already some information. Some C, I don't remember what they had, honestly. This is based on some very nice coupling argument, quite simple actually. It's totally insensitive to the shape of the domain. And later, there was a very nice paper by David Wilson who considered a different type of dynamics with somehow non-local, for which he could prove actually the conjectural L squared log L bound, but for these other dynamics. All right, this is about somehow fast mixing type of result. And you see, so here there is a result are really insensitive to the type of the domain. And if you somehow what experience showed is that if you want to go further, you have really to go a bit deeper into the geometry of the problem. Okay, and I would in the last few minutes I would like to mention 2 or 3 more recent works. One of which is still ongoing, but almost done. So the first one was the first example where we could get a mixing time for this zero temperature 3D Ising dynamics of the correct order, L squared, up to smaller order corrections. This is a work from 10 years ago with Pietro Caputo and Fabio Martinelli, and essentially gives you the optimal result, but up to a very important restriction, that is that we work in domains such that the limit shape is affine. So now, if you remember my picture of the cylinder, etc., if you fix the Dobrushin boundary condition by intersecting this cylinder with a plane, okay, some tilted plane, then you will get some boundary condition like this. And then you can easily imagine that the limit shape you get when the size of the cylinder goes to infinity is simply a plane that, is the same plane by which you intersected your cylinder.
Frozen.
No, it's not frozen because the measure is still rough. But if in terms of limit shape, the limit shape is simply a plane, a fine. But frozen would mean a horizontal plane. It's not frozen, but it's simply, in a sense, a trivial limit shape. It's just a plane. Okay, so and for instance, in the case of this picture, it would be just a 1-1-1 plane.
What's the difference between your two inequality signs?
Again, sorry.
In the statement of the theorem, there are 2 different inequality signs.
Sorry. I think what we can prove is that now, the one is simply here. We simply have a constant, and here, this is I was not very specific on the little of 1. Actually, okay. If you want what we have in the upper thing, we have also a constant times L to the 2 times log L to the B12 or something like this. Yeah. Okay. Yeah. So this is the.
So we want to be observed case. This is
well, we don't, but this is what we could do 10 years ago. To somehow the only situation in which we could control this mixing time was assuming that the limit shape is affine, which is very restrictive on boundary conditions, but this is what we could do. Of course, we would like to treat the case where you don't where the limit shape is some curved thing, which is much more interesting. Okay, but this is what we could do at the time. Right. So this assumption of affine limit shape is very special. And why is it special? Because what it happens is that in the long time regime, you start getting closer and closer to equilibrium. And since the limit shape is affine, you can somehow compare your measure with infinite volume translation invariant measures. So this is, okay, I cannot explain how, but somehow it's really essential. Okay, then something I got with Benoit Laslier, who is here a few years later, is that we could go beyond this assumption that the limit shape is affine, but we couldn't get really the result we wanted. That is, what we could prove there is that somehow you're in a situation now where your limit shape is somehow curved. You have to imagine this is a section of the limit shape. And what we could prove is that if you wait a time which is the correct order, like L to the 2 plus a little bit more, you are very close. The height function will be typically very close to the equilibrium shape. But very close simply means that if this thing is of size L, then you are within epsilon L. Which is somehow you're macroscopically very close, but in terms of equilibrium, you are super far because typically you should be within square root of log L from it at equilibrium. Okay, but still, okay, this was already quite non-trivial work to show this, and it was. But as you see, it implies nothing on the mixing time, because actually what happens in reality is that it takes like order L squared time to get epsilon L away from the limit shape, but then it gets as much and actually a bit more to get very close to equilibrium. So in a sense, in terms of mixing time, this result isn't saying anything. And so, and what we are about to finish now is a proof that of the almost essentially sharp up to logs, say, result on the mixing time. Oh, I forgot to say something essential. In both of these theorems, we are assuming, making one assumption, which is a restriction, that the limit shape has no facets. These facets are really, I think there is something new happening there. So we allow for limit shapes that are curved, as you like, but we don't allow for facets.
Facets are the frozen.
Yeah, frozen regions. We don't want frozen regions. I mean, we would like to, but we cannot. Okay, so here I will not say anything about the proof, but let me just say that an extra ingredient we use is some very sharp and quantitative estimates on equilibrium fluctuations for the height in domains, like mesoscopic domains with kind of general boundary conditions that were obtained by Benoit very recently, and there are estimates in the same spirit by Rick, but somehow we needed something more quantitative than that.
You have about 7 minutes.
Okay, that watch is...
That's ahead of time, and plus you started later.
Okay. Okay, well, but... okay, very good. Well, I'm still... I rushed so much that I think this 22 is actually cheating. I have some extra slides in case you have, but okay. All right, so this is the result. So we have this almost optimal up to the same type of precision as for the affine limit shapes. But now remember, the intuition, the conjecture would be that this height function rescaled diffusively would converge to the solution of a certain nonlinear elliptic parabolic PDE. We cannot prove that, obviously, because we cannot even we cannot get rid of this little of 1. So obviously we are far from proving something like this. But somehow the intuition behind this conjecture is really helping the proof. So we really use the intuition even though we don't prove this conjecture.
Is the equation strictly parabolic, or do you have to worry about it being, is it uniformly elliptic?
Yes, if you exclude if you don't have frozen phases. So this.
So the frozen phases give you the.
Yeah, right. If you are close to this is why I think something new is something. If you write down the PDE it becomes singular at near the frozen boundaries. So somehow the mobility goes to infinity, but then some coefficient go to 0. So it's even at just a PDE level, I wouldn't know what to do. Okay. Right. So actually, I would like to finish with a few open questions for the future. There are many, but I just selected two. Well, the first one is kind of obvious continuation of the last theorem I mentioned. That well, somehow, what is the interplay between these facets or frozen faces and the dynamics? Personally, I still think that the like L to the 2 plus little of 1 result on the mixing time should hold even when you have frozen faces. I'm not totally sure, but I guess something some new phenomena will appear. For instance, already the fact that at equilibrium the fluctuations are really different close to frozen boundary will play a role. So, but somehow understanding this point is, I think, quite interesting. The second point is it's very different. So I wanted to mention this because I think it's a very nice open problem. So forget about infinite temperature. Now just think of being at beta larger than beta C, but not infinite. And I didn't introduce a spectral gap, but I guess you can, okay, you know what it is. Otherwise, it's simply, the spectral gap would be simply the gap. You look at the generator of your Markov process. It has an eigenvalue which is 0 just because the probability is conserved. And there is a first eigenvalue next to 0, and the difference, okay, the distance is the spectral gap. And this gives you how fast you converge to equilibrium in L2 distance.
And this is not related to the mixing.
It's related. There are inequalities between them, but it's not like they are. Okay, morally, the gap is an inverse of a time, so you could compare the inverse of a gap with the mixing time. There are inequalities, like the mixing time is always larger equal than that, than the inverse gap, and it's smaller equal than the inverse gap times log of.
Because you define the mixing time with the total variation distance rather than something else, or it's just always different?
I think the difference is because mixing is from the worst boundary initial conditions, while autocorrelation assumes that you're already close.
It's very different. So here you look at L2 convergence. So in a sense, it's not like you don't see very unlikely initial conditions, but really, as I was saying, so in mixing time, you really take the supremum of all initial conditions. In mixing time, you essentially look at convergence to equilibrium starting from stationarity. So it's really two different things. In some cases, they are of the same order, but there are really cases where, for instance, if you look at the simple random walk on an interval, for simple exclusion, yeah, anyway, so it's simple exclusion, the mixing time is L squared log L, and inverse spectral gap is L squared only.
Simple random walk on a cycle.
Yeah, okay. So, yeah, but they're comparable somehow, but this is, for instance, an example where they are very different. So if you look at the spectral gap of the Glauber dynamics at beta larger than beta C with plus boundary condition in a box of size L, we expect the mixing time to be L to the 2 in all dimensions. But about the spectral gap, we expect it to be over 1 over L in dimension 2 and over the 1 in dimension 3 and higher. Well, I'm not totally sure about dimension 3, but certainly in higher dimension. So, okay, so correspondingly, if you look at, maybe more intuitively, if you look at the autocorrelation of the spin, so you look at the spin at the origin, in the infinite volume dynamics at some temperature beta at equilibrium, in the stationary case, you look at the average of the spin at time 0 and the same thing at time t. Obviously, for t going to infinity, the two things decorrelate, this tends to 0. And it's expected in dimension 2, it goes to 0 like a stretched exponential. It was conjectured by Fisher and Hughes like in the 80s. And in higher dimension, it should be exponentially converging, exponentially fast.
So why do they uncorrelate? I mean, isn't it the pure phase?
Oh, I'm sorry. I'm sorry. Yeah, you're right. I should subtract m squared. Yeah, of course. Yeah. I forgot the semicolon. Yes. Well, they correlate, but yeah. Yes. And actually, so this is quite open. For instance, in dimension 2, the best we that can be proven. There's a lower bound. Here they almost, okay, there was a paper by Bodino and Martinelli in 20 years ago where they essentially proved the lower bound. There are some log corrections in the exponent, if I remember well. And the upper bound, this is the best we have with, that is kind of corollary of something we did with Eyal, Fabio, and Alan. So you see there is a lot of room for improvement. It's not as good as an extraction exponential in dimension 2. And for instance, in dimension 3, nothing. So this, I think, is also a very nice open problem for the future. And now I'm also officially out of time, so thanks. Yes.
Imagine I take 5 to the 4th in the limit of Ising, and I just make the evolution of the equation of motion. The system will thermalize. Has anyone compare with the Glauber dynamics?
I'm not sure. Maybe Roland. No.
So I'm not sure. So
You think of the limit where the spins become,
I take the continuum limit a priori. I go on the limit 5-4, which is Ising, and I let it evolve.
Well, depends. I mean, I guess
how do you let it evolve?
Well, equation of motion.
like
That's
Langevin.
like Hamilton.
No. Purely determinism.
No.
But it's in the same universality class, should be.
But I would like to know how.
No, but what do you mean purely deterministic? So you just tends to the minimum, so it's not tending, it's
No,
not
not
thermalizing.
to the, I mean, the rule of the game is you fix the energy macroscopically.
Okay. Like
So this is the equivalent of your T, and let the system evolve. So
on the shell of, say,
The nonlinear Schrödinger evolution.
equation of motion, Laplacian plus interaction, phi cubed,
yeah, but with fixed energy.
energy.
No, I don't think it has.
So what happens is that the mode, you prepare the system in certain mode, they start spilling up to filling at equilibrium all of them. So this is what happened. So I'm just curious
I
if
don't think
someone
so.
has ever compared the two kind of evolution.
No, I don't think so.
Other questions?
I don't think so.
So if I take the Ising model at 0 temperature and put a cubic box of size L, do your result imply a bound on the time of disappearance?
Okay, so this is where the extra slides are useful. So, it's actually a question. So you look at the cube, plus of pluses and surrounded by minuses. This will eventually disappear at 0 temperature. And the question is how quickly, how fast. And the conjecture is that it disappears in a time L squared in all dimensions, as you know. And what we could prove is that, in fact, in 2D, not only it disappears in time, essentially L squared over 4, but also you can follow the evolution. And in higher dimension, what we can prove is that the disappearance time of the droplet is between L to the 2 plus little something and L to the 2 over log. But actually, this comes before this results on the mixing time. In a sense, it's easier because it's easier in the sense that the difficulty of mixing time is that as time evolves, you're getting closer and closer to these non-trivial limit shapes, while here the thing is just disappearing. So in this sense, it's a bit easier in a sense. But so I cannot say it's a consequence of what we did. It's rather doing that we learn a lot of things that then we use now for the mixing time.
It's at 0 temperature.
It's also 0 temperature, yes.
Are there also results in the sort of microcanonical ensemble where you fix the
number of spins, or
no, you fix the magnetization, so to say.
The Kawasaki dynamics.
Yes.
Yeah, I was going to say very little, but yeah.
That's very slow. Extremely slow.
Yeah. Well, there are things like metastability type of results for very extremely, like beta growing very fast with L, but not too much.
Okay, then we have a break, till 11, which